So good morning. Lombe Mutale. For those who don't know, I've got a speech impediment, so I have to speak a bit slow. So this presentation is based on a dissertation which I just completed. The outline of the presentation is as follows. I'll briefly discuss challenges and opportunities in the construction industry. I'll talk about shell structures and the perfectum principles. I'll go through the methodology, especially focusing on the parametric modeling and computational design, after which I'll show you the case study and the conclusions. Research has shown that the construction industry is lagging behind in terms of productivity, growth, digitalization, and sustainability. This is compared to other industries. So part of the reason for this is that most structures are made from steel reinforced concrete. But steel is prone to corrosion, which leads to disintegration of the concrete, and it affects the durability of concrete structures. It is possible to make concrete only structures if they are compression only, such as with a 2,000-year-old concrete pantheon in Italy. This increases the durability of the structures. The World Economic Forum has suggested some ways to improve the construction industry. Some of these include firstly through digitalization, such as with the use of building information modeling, which increases interoperability and collaboration between the stakeholders. The second of these is through material optimization and sustainability, such as with the use of innovative materials. The third is through construction systems optimization, such as through prefabrication of structures. Vernacular shell structures, which were the focus of the dissertation, have the advantages such that they're aesthetically pleasing. Second, they have long spans, which don't require intermediate supports, such as seen in Figure 4. They also have high strength to weight ratio, and they can be compression only, which means that you don't have to have steel reinforcement in the structures. However, they have some disadvantages, such as the cost of the formwork and the scaffolding, the setting up and dismantling of the formwork, such as seen in this figure here. Additionally, if the shell structure is too thin, they are prone to buckling. And finally, they're quite complex to design. But this complexity it's possible to it's possible to overcome this complexity through form finding, as well as through using finite element analysis. Perfectum principles were theorized in 2019 by Xenia to address some of the challenges that have been highlighted. These principles include having sustainable low-strength concrete compression-only system, which is self-supporting or has just a few supports during construction. It is a precast system with panels sized about a meter, and 300 meters thick, and it is composed of durable and long-lasting PT cables to connect the blocks. So for this reason, the main research aims for the project were to firstly to define a BIM-based framework for collaborative design between the two main stakeholders, the structural engineer and the architect. Secondly, to perform parametric modeling and computational design, including form finding to produce the compression of the structure. Thirdly, to define custom interoperability tools. And finally, to perform structural analysis to assess the behavior of the proposed construction system. The framework which was produced consists of 3 processes, and it's simplified to a project with only the architect and the structural engineer. For the first process, geometry definition occurs, starting with the client requirements and a concept sketch by the architect, which is discussed with the engineer to come up with an initial shape in Rhino. In the second process, the BIM model is defined, and further information is added. This model is then connected to the structural analysis software, where the geometry is reproduced using custom tools. And finally, the structural analysis is performed in Diana. The parametric modeling and computational design was carried out using the visual programming language Grasshopper 3D. The process involved firstly defining a planar surface, and then defining a network of particles and lines. An upward force was assigned to the particles, and a stiffness was assigned to the lines. This information was then input to the Kangaroo physics solver, resulting in a 3D mesh, as for instance shown in the picture. Thereafter, this same information was used to create lines which represent the PT cables in two directions. The surface was further tessellated to have individual blocks and thickened. Then a cellular automata algorithm was set up to be related to the chosen construction system for the panels and the PT cables. A case study was set up to assess and evaluate the proposed methodology, as well as the proposed framework. The case study consisted of four curves, two short and 2 long curves, which is following the process just described, resulted in a planar surface. the supports were chosen to be at either end of the structure as shown in the figure. And this surface was further divided into a 14 by 10 network, so that the resulting individual blocks would be approximately a meter by a meter. This information was fed into the kangaroo physics solver, resulting in this 3D mesh. After which the process described previously was followed, and the surface was thickened for a 300 millimeter result for the panels. For the cellular automation algorithm in Grasshopper, for this particular case study, the construction sequence selected was to have the sequence starting from the inner lowest blocks and then outwards to the top of the structure. So what this means is that each construction stage refers to the addition of a new block and its respective PT cables to the structure. So for instance, at stage 29 individual blocks have been added to the structure following the chosen assembly sequence. For this process to work, it was necessary to have plugins and custom interoperability tools to and from the BIM platform. For the first part, plugins are available to ensure that the geometry from the 3D model to the BIM model is kept intact, especially using the Rhino Inside Rivet plugin. However, for the next process, it was necessary to create custom tools to transfer the geometry from the BIM platform to the structural analysis platform. This required accessing the Rivet API to create a custom Python script, as well as a further Python script for the automatic definition of the properties, as well as for the phased analysis. Following boundary conditions and material properties for the finite element analysis were followed. As mentioned, the permanent supports were chosen to be on the short curves, and provisional supports were set up on the middle of the structure. Wind loading and snow loading was also applied to the structure, and 30 MPa concrete and 450 MPa steel were chosen for preliminary checks of the proposed construction system. The finite elements analysis results show that during construction, the stresses stay below 1.35 MPa design tensile strength. This is also the case after construction, when the wind loading and the snow loading were added and the structure was checked for the ultimate limit state. In conclusion, it was shown that it's possible to set up a framework for parametric modeling and computational design to achieve interoperability and collaboration between engineers and architects. It was also shown that it's possible to have material optimization and sustainability by foregoing steel reinforcement to increase durability. And third, excuse me, optimization of construction systems is possible by using prefabricated panels and an automated construction system. And for future research, we would like to look into optimizing concrete mix design by using sustainable materials. And for the system to work, it will be necessary to have technological advancements for panel molds, as well as for the detailing of the proposed PT system, including connections for the provisional supports and assessing how the structure would behave with more robust load combinations. Thank you.